Hello everyone, I'm Mr. McBrien. This is SCH4U, Corrosion. Alright, so for today, I'd like to start with a question. I'd like you to think about what's more dangerous. The subject of many of our nightmares, a great white shark, this cute guy, a hippopotamus, or corrosion, the oxidation of various metals. Okay, so the Ontario curriculum asks us to be able to explain corrosion of metals in terms of an electrochemical process and to be able to describe some common corrosion inhibiting techniques. And that's what we're going to do today. So why do cars rust? We've all seen these kicking around. As a matter of fact, I've driven far too many of them, in my opinion. So a common name for an older car is a rust bucket, right? We've all seen them driving around, and to be honest, cars are much better than they used to be. And we're going to talk about some reasons for that soon. But in the end, cars rust. Corrosion's about a lot more than cars. So of course there's trucks as well, ships and aircraft. And remember, if something goes wrong with a car or a truck, you might be stranded by the side of the road. You'll be a lot more disappointed if you have some kind of catastrophic failure in a ship or in a plane. Beneath the surface of concrete, we have what's called rebar, reinforcing metal inside concrete. Of course, near and dear to our hearts in Canada are pipelines and gas distribution systems. Electricity is also about metal, right? And the rails, sewers, manufacturing equipment, much more is subject to corrosion. And corrosion is so prevalent that of all the iron smelted around the world, 20% of it is done just to replace iron that has corroded. In fact, I was able to find one estimate online that suggested that the costs associated with corrosion in 2016 were $1.1 trillion. So obviously corrosion is a concern. And it's about more than money as well. So a very fast cursory search online, I was able to find an article about 52 workers being injured in Regina when corrosion caused a pipe to rupture. Bridges do collapse. Even in the first world, we have bridges collapsing. So I found an article about Connecticut Bridge collapsing. So in terms of the original question that I started with, what's more risky, what's more dangerous? An estimate I was able to find put the death toll from great white sharks at less than 10 human beings per year. The hippopotamus, much more dangerous at 2,900 deaths per year. But corrosion, one estimate I was able to find, put it comparable to the hippopotamus at about 2,000 deaths per year attributed to corrosion. And to be honest, that probably ignores some failures of systems inside cars, like suspension systems and things in cars where it's hard to attribute those. But in any case, what we can say is that corrosion is much more dangerous than the great white shark and comparable to the hippopotamus in terms of risk to human life. So if you were thinking about having a nightmare about a great white shark tonight, well, you might want to think about corrosion instead. So it's a good idea for us to understand it. There's lots of money at stake if you're a Republican. There's lots of lives at stake if you're a Democrat. So what causes corrosion? How does it work? And how can we prevent it? Well, that's the subject of the discussion today. And happily, yesterday we talked about reduction potentials. So let's look at them. We have a reduction potential here for oxygen in the presence of protons to produce water. And that reduction potential is at 1.23 volts. There is only one metal that has a reduction potential higher than this. And of course, most of you have already picked that out. So only gold has a reduction potential higher than oxygen. And I'd invite you to think about what's special about gold. So down below oxygen, we can find silver, copper, iron, aluminum, magnesium, and all the other metals. Well, what's special about gold? It doesn't tarnish. It doesn't oxidize. So your grandmother's gold jewelry looks just as good today as it did 60 years ago. Every metal except gold oxidizes. So the precise behavior, the precise way that oxidation, that corrosion occurs, depends on the metal. But what we can say is that our original subtitle of our discussion today, well, we can say rust just doesn't sleep. Okay, but there is corrosion and there is corrosion. Some of you may have observed that when you travel to some place like Texas or San Diego, you'll see a lot of older cars driving around that you would never see here in Ontario. We can understand that in terms of the anatomy of rusting. If we look at the process of rust on the surface of our 1976 Ford Pinto, we can get some interesting insights. So rusting is actually an electrochemical reaction, of course, oxidation of iron. But remember that for every reduction there has to be an oxidation. For every oxidation there has to be a reduction, right? So the question is, if iron's going to be oxidized, what is going to be reduced? And the answer is right here in this display. So we can see iron, metal, being oxidized and giving up electrons. And the question becomes, what accepts the electrons? And that's where things get interesting. So this is actually the full story of rusting right here. What we have, we need air, we need water, and we need oxygen. So the other side of this anode reaction of oxidation of iron is the cathodic reaction, where water reacts with oxygen and accepts those electrons from the iron to produce hydroxide ions. Now this is interesting, right? Because this means we have a whole lot of things that are necessary in order for us to achieve this oxidation. We need liquid water, we need oxygen, and one more thing. We need to do something with all this hydroxide. So based on equilibrium theory, what's the effect going to be on if you increase the amount of protons kicking around? Well, the answer is the protons will get rid of the hydroxide, and they'll keep, according to Le Chatelier, keep pushing this reaction to the right. In other words, if you put acid in this water, it will speed up the process of oxidation even more. So many chemists have this conversation. Lots of people will tell you that salt water is corrosive, and in fact it's not. Salt water isn't corrosive, but the process of corrosion requires a salt bridge, right? It requires this completion of the circuit. And water with lots of salt dissolved in it is a perfect salt bridge, and it further facilitates that process of corrosion. So if we're looking at why in Ontario our cars rust a lot in the wintertime when we put salt on our roads, the answer is we're providing the process of corrosion with the perfect salt bridge. And this is why in places like San Diego and Texas, they don't have problems with cars rusting, and you can see some amazing old cars in great shape. And the reason is, A, there's no salt, but B, there's a lot less water kicking around as well. So if we're stuck here in Ontario, what do we do to fight corrosion? Well, there's really only two ways to fight corrosion. We have to exclude oxygen and water, or we have to prevent the flow of electrons. Excluding oxygen, well, we're pretty clear on what we can do for that, right? We can keep oxygen off the surface of the metal by painting it and by keeping it painted. So if we have stone chips on the hood, you go ahead and touch those up. Many of you will have seen the Crown rust protection advertisements. Well, another way to keep the oxygen and the water away from the surface is to use a thin coating of oil. And that oil further keeps oxygen away. Now there is another way to do this, and this is rather interesting. So you can keep oxygen and water off of the surface of various metals with oxidation products. And so this is the reason why we have much less corrosion around aluminum, stainless steel, and magnesium. It isn't that they don't oxidize. In fact, what occurs is these metals oxidize very quickly, but the oxidation product, the oxide, sits on the surface and keeps oxygen away. So this is like a natural coating, like its own kind of paint. So they don't seem to oxidize, but what we're really looking at is a very thin coating of the oxide on the surface of the metal. Okay, so another way, instead of coating it and excluding oxygen, there is another way that we can prevent the transfer of electrons. And that's with the idea of what's called a sacrificial anode. So we're aware that the process of oxygen being converted into hydroxide requires electrons. Well, those can come from the metal about which we care, or those electrons can come from somewhere else. And we call this a sacrificial anode. So here is a structure that we want to protect. And let's say it's in seawater. It's going to be very difficult to keep water away from the surface of this metal. So if we want to protect this from corrosion, we have to do something different. Notice that even if we paint this, sooner or later there'll be scratches in the paint, and it's very difficult to repaint it because it's under the surface of the sea. So instead what we do is we take a large block of aluminum and we connect it via a wire to our metal we want to protect. Now, as oxygen is converted to hydroxide, in the same process we saw previously, instead of the electrons being provided by, let's say, iron in this steel in our structure, the electrons come from the aluminum anode, the sacrificial anode. And slowly that anode oxidizes away. And this protects the iron. Now what's cool about this is that we can, once in a while, we can look down there and say, oh, okay, well, it's still there, we're good. We can maintain it. And if after say a decade that aluminum has dissolved away, we can go ahead and wire a new piece of aluminum to our structure. It may not be cheap, but it's a lot cheaper than building a new structure. It's a lot cheaper than having a highway collapse into the sea. Okay, one of the key things here is this metal that we use, the sacrificial anode, has to have a lower reduction potential than iron. Okay, there's another way for us to prevent electron flow from our metal that we want to protect. And this is in fact done by using an opposing potential to push back the flow of electrons. So we can do this for certain systems we want to protect, let's say a bridge that we want to protect. What we can do is attach a power supply, and it pushes a voltage against the oxidizing voltage to prevent that cell from allowing current to flow. So electrons are pushed back onto the steel. They aren't pulled away. So this is essentially an opposing potential. Now what's cool about this is that modern systems these days can be solar powered, so that potential can be provided by the sun. So if anybody ever tells you that they're planning on building a solar powered bridge, that can absolutely be the case. All right, now there is another option on how to protect our metal of choice. And this actually kind of combines both of these concepts we've just seen. Galvanization is a process by which iron is coated with a little bit of zinc. And you've probably seen galvanized metal before because it has kind of that hazy look to it. When we do this, we accomplish two things at once. It protects the iron from corrosion because the zinc oxidizes more easily than the iron. So the zinc itself provides a sacrificial anode. Just like that aluminum for the pier that we showed earlier. Now, the zinc oxide, though, works like the coatings on those magnesium rims we talked about earlier. Zinc oxide isn't soluble in water, and it clings to the surface of the iron. So what this does is it keeps any further oxygen from getting to the surface. So galvanizing iron accomplishes two things at once. And we can see the kind of effect of it right here for a galvanized versus non-galvanized piece of metal. It dramatically improves the corrosion resistance of iron. And the good news there is you don't really need to restore that. That'll last for decades. Okay, so let's sum up. Virtually all metals are subject to oxidation by atmospheric oxygen. And the cost of this is amazing in terms of lives, in terms of money, corrosion costs. Now, standard corrosion of iron and other metals is an electrochemical process. And that electrical chemical process is dependent on both water and oxygen to proceed. So we can combat that by acknowledging its electrochemical nature, or by simply excluding water and oxygen from the surface of the metals. Okay, so for your homework, please go ahead and work on the worksheet and maybe think about one follow-up question. Let's say that you're talking with someone about engineering an underground iron oil pipe. What characteristics would you look for in a sacrificial anode, and how would you design it? Okay, thanks very much. Have a great night.